Okay, welcome to the NUPOC Video Study Guide number 9. Let's look at question 8 in this video. We're going to look at the first part of question 8, so if you're following along with the guide, you'll see that question 8 actually asks for three things. Basically a brief discussion of the Fourier series, the Taylor series, and the Laplace transform. So instead of one long video, let's just break it up and let's talk a little bit about the Fourier series here. So the Fourier series is basically just a tool that we can use to decompose a periodic signal, any periodic signal. So f of omega t, where omega is the fundamental frequency of this signal. And we can decompose that into an average value, we'll call A0, and an infinite sum. And that's going to be an infinite sum from n equals 1 to infinity. I'm just going to write it out first, of an cosine n omega t plus bn sine of n omega t. So basically what this says is that any periodic function can be broken down to its average value and then a sum of sinusoids. So a lot of people probably know this intuitively, without even really thinking about it, but any signal basically can be represented as a combination of higher order frequencies. So for example, if we have some signal, let's just draw one out here, right? And let's say our signal does this. It's periodic and it's this bipolar square wave like this. Okay, so there's some sort of fundamental frequency here. You can see, right? But that doesn't completely, approximate our signal. So there are some higher order frequencies here as well. And the great thing, the really cool thing about the Fourier series is that it can tell us what the amplitude is of each of these higher order harmonics. You can see here, so these are the even harmonics and these are the odd harmonics. You can sort of get that by understanding that cosine is an even function, or a function with even symmetry, and sine is a function with odd symmetry. And they are at integer multiples, each of these harmonics, right? These are the harmonics here. They're at integer multiples and multiples of the fundamental frequency omega. And what the Fourier series allows us to do is to find all of these ANs and BNs, which are the amplitudes of each of these harmonics. So it basically allows us to say, okay, given some periodic function, f of omega t, what's the relative strength of each harmonic, or what are the dominant harmonics? Or it allows us to say, okay, we have a lot of frequencies in this area but not in this area, or we have a lot of odd order frequencies but no even order frequencies. So it's a really great tool. And one of the cool things about being able to do this kind of frequency analysis is we can just do a quick example right here. Is it allows us to see that even though two functions may have the exact same fundamental frequency, they may actually have very different harmonic spectrums, or a very different composition of these harmonics. So an example would be if we looked at this function right here, right? So let's kind of extend it back a little bit, and let's say it does something like this, right? Okay. So let's say now that we have another function that has the same omega, so the same period, right? So let's say it starts right here, okay? Or better yet, let's start it at 0 here, right? And we're going to go all the way from here out to here, so that's one period, right? Like that. And then it starts over, it goes for another period, and then another period, right? And then it would do something like this over here, right? So these two functions, this bipolar square wave and this sawtooth wave, each have the same fundamental frequency. But if you put them into the Fourier series, you'll find that their AN and BNs will be totally different. And in fact, we can see right away something that will be very different is their A0. Because this function here, this square wave function, right, it's completely AC. If you integrated it over an integer number of periods, you'd find that there's no average value, so its A0 would be 0. Whereas this sawtooth function here, you can see right away that it never goes below 0, and so it has some sort of average value here, which we could calculate using geometry, but we could also calculate it using our formula for A0, which we'll get to in a minute. But you can see that it has a non-zero A0, so it has an average value. Also note that this function here, right, has odd symmetry, right? See, it has odd symmetry. F of x equals minus f of minus x, okay? So there's no way that we would have any even symmetry functions representing it. So we will have no ANs. So in fact, this square wave here, if we took the Fourier series on it, we would find that we would only have values of Bn and sine n omega t frequency components. Whereas here, we don't have any symmetry at all. If we looked at some f of x, it doesn't equal f of minus x, so we don't have any even symmetry, and we don't have any odd symmetry either. So in fact, we would have A0s, ANs, or NA0, ANs, and BNs in this function here. So it's really cool. So the Fourier series allows us to look at all kinds of periodic functions and determine their frequency composition or their frequency spectrum. So let's just touch on real quick how we would actually calculate these A0, this A0 and these ANs and BNs. Okay? So A0, that's just the average value. So that's just going to be the integral from minus t over 2 to t over 2 over 1 over t, or times 1 over t. So that's just the integral over a period divided by a period of our function, f omega t d omega t. Okay? Our ANs and our BNs are a little bit different. Our AN is still going to be the integral over one period, but we're going to divide it over half a period, and we're going to multiply our function by cosine n omega t before we integrate. Similarly, with our BNs, that's going to be the integral over one period divided by half of the period, and we're going to multiply our function by sine n omega t before integrating it. And so if you wanted to find a of 1, you would substitute in 1 for n here, and you would do out the integration, a2, substitute in 2, etc., etc. And if you were to take the infinite sum, you'd find that this equality would be true, that you could actually exactly represent your function f of omega t with this Fourier series. But for practical purposes, right, you would only want to take maybe the first 3 or 5 or 7 or 13 or whatever number of harmonics, and at some point it will become a good enough approximation for your purposes. And so something else to touch on here is, you know, when we get these AN and BNs, it's essentially telling us sort of it's related to the power at each of these harmonics, the amount of energy at each of these harmonics. So if some of you have ever seen, say, a spectrum analyzer or you know, an FFT on an oscilloscope or in some sort of simulation software, you know, it probably gives you some graph like this. I'm just going to say this is somehow related to the energy U at each of the harmonics. So you could see, say, for a function like this f omega t here, you would have some DC value, right? So it would show you an impulse at omega equals 0 for DC value. And then you would have some sort of some power at the fundamental frequency, and then you maybe would have all these harmonics going out to infinity, or however many are calculated. So the amplitude of all these impulses are related to your ANs and your BNs, right? Because if you have some frequency here, you know, let's say this is the fundamental, that's at, you know, cosine omega t, and then this is maybe at, you know, cosine 2 omega t or something like that. So this is the harmonic, and then the amplitude of these impulses will represent your amplitude, so your ANs or your BNs or something like that. So the Fourier series is essentially just a really neat tool that we can use to take any periodic function and then decompose it into its frequency spectrum and look at how much energy is at different frequencies and whether or not it has an average value. And one of the really cool things that it shows is that you can have two functions with exactly the same fundamental frequency, but widely different harmonic composition, or a widely different frequency spectrum.